Hello everyone, and welcome back to the Quarantine Lectures. Dr. Heinz with you here again. Before we get into the last discussion and kind of going through some sample problems, I wanted to do a real quick review of torque and levers. So levers are something that you've probably already seen in some of your other physics courses over the course of your education. The lever itself is really just a simple machine, and from it actually a lot of other machines are derived. But what we can do on a lever is we can achieve a multiplication of force. So what we see right here is a basic lever. I do want to point out a note here that the reason that those forces are at an angle coming off perpendicular to the board is actually important. Okay, so the conservation of energy still applies. We can't create or destroy energy, right? But our input force here can cause a greater output force based on the distance it is away. So in this case here, we have just really the equation for our lever, which is the energy input equals energy output. The force times the distance from the fulcrum equals the force times the distance from the fulcrum, right? So input force times the distance equals output force times the distance, right? So what does this really mean if we take it, if we're looking at this to take away? What it means is that we can put a smaller weight on a shorter lever and lift a larger weight that's on a much larger lever, right? So in theory, if you were to get a board that was long enough or strong enough, we could push down just with ourselves, or we could stand on it and we could lift a car, okay? All right, so now torque, just a real quick review of torque. Torque is the rotational equivalent of the linear force that we deal with on a regular basis in like our physics classes. Torque is noted with the Greek letter tau, right? It's that little curly guy. And torque equals to the force applied times the lever arm. That's really just what we saw in the last slide with our lever. Now, it is important here to understand that the lever arm is the perpendicular distance from the axis of rotation. So to point out what I mean, let's look at this, right? In the two previous examples, we saw that the forces were perpendicular to the board itself, right? But let's say we were to actually put, instead of us pushing on it, let's say we were to put weights on each side of the lever, which is something which is very common, like in a seesaw. The input force there would actually be gravity, which is straight down. So in this case, it's not the length of the board. It's actually the distance from the fulcrum. Right, so that's where our trig comes in, and we have to be able to calculate that. In this case, when it's going down, the actual lever arm is going to be shorter than the actual length of the board in this case. So remember, that is important, that it's not necessarily the actual distance if the board is at an angle, for example. So what we're looking at in this example is a wrench on a nut. So remember, we're talking about the lever arm is the perpendicular to the force, right? So in the case of the wrench, if we were at 90 degrees, we were pressing down on that wrench straight, we would be able to use the entire lever arm of the wrench. However, as you guys know, when that wrench is going around, it'll actually kind of make a rotational motion. So in the second example we see here, let's say we're at 30 degrees, the lever arm itself is only 8, which means that we're only getting roughly 80% of the force there, right? And in the case, I mean, obviously you guys know that if you're using a wrench, you don't push against the wrench into it. That's because you don't get any torque out of it at all, right? Because in this case, what's happening is the force that's being applied is actually in the plane that we want to rotate on. So we're getting no torque on there, right? So the takeaway here, of course, is, as we were implying, the force produces a maximum torque when it's completely perpendicular. Okay? Just going into a couple different levers which will apply for some of the stuff that we're talking about a little later. We also have a second class lever. Now, second class lever, right? The lever we were looking at before was simply just a fulcrum and one weight on it. A second class lever is, let's say we had a long board with a weight in the middle, and we were to go outside on the other side of the fulcrum and do some force to try to lift that. Okay, what you're going to find is that the input force is much less than the load, meaning that we could lift a larger load with less force. Hey guys, so we're out here in front just to look at difference between second class and third class levers. So our weight is going to be this big heavy paint can here. So if I want to do a second class lever, what I'm going to do is I'm going to get on the end here and just lift like this, right? Relatively easy for me to do. Now the reason that this works is because I'm lifting at a much higher or a much farther distance here. Remember, and the equation for work is force times distance. So for this to be equivalent to a much smaller distance here, obviously I have to put in less of a force than I would if I was lifting that directly for that distance. Okay, now on the flip side, the third class lever, I'm going to be lifting here, and now our weight is on the end, right? So what I have to do is I have to apply a force here that's going to go a smaller distance than the weight on the end well, which means that overall I'm going to have to apply more work here in this location, right? So if I get down, I'm lifting here now, and you can see it's significantly harder to do, and I'm not just faking it. There we go. So I had to actually cheat and get higher to do it, right? So from the lever standpoint, it takes a lot more work to do it in this location than if we were to go back to our second degree level or our second class lever and lift in this direction. That's how that works. In the case of a third class lever, which we see on the bottom, it's really kind of flipped around. So instead of having the weight in the middle and us be on the outside, now we're actually pushing up from inside to try to lift a weight on the outside. And in this case, we actually have to put in more effort than what we're trying to lift. However, this inherently sounds kind of dumb. Why would you try to do that? I want to bring us to a biomechanics example here. This is actually how our bicep works, right? Our bicep, think about it, right? If we're trying to lift a weight out here, right? Say we're in the gym, we're getting all swole. We have a weight here, we're trying to lift it. Our bicep is attaching and trying to lift our arm right here, right? So we are actually right here with our arm using a third class lever. So this does matter for biomechanics. All right, now next, let's just go ahead and do a quick review of what we talked about, right? So if we were to look at this example here, we have an input force at D1, an input force F2 on the outside, and then the load in the middle. The input force F1 would have to be much higher than the input force F2 because F2 is on the outside. All right, so that's pretty much it for torque and levers. So now we can move forward to the final lecture in the series.